Excellence. Let us
Nurin,
embrace
Nurin.
this opportunity to learn from one another and strengthen our shared community by advancing STEM education and harmony with environmental and cultural value. By saying Bismillahirrahmanirrahim, I officially declare the second chemistry edition and chemistry summer school open. Thank you much. I wish you all an entertaining and inspiring experience during this summer school. Assalamualaikum warahmatullahi wabarakatuh. Salam.
Thank you very much for your warm and inspiring words. May this event be a fruitful learning experience of all of us. Now let's begin with our first speaker. We are honored to welcome Dr. Seamus Delaney from Deakin University, Australia. He will deliver a session titled System Thinking in Chemistry for Sustainability. The session will be moderated by Dr. Ari Syahidul Shidik, lecturer at Chemistry Education Study Program, Universitas 11 Maret Indonesia from 2022 present. Passionate educator and researcher with research interest in STEM education, ESD, and systems thinking. He is committed to innovative teaching methodologies and addressing contemporary educational challenge. Enthusiastic collaborator with a drive for lifelong learning and a dedication to creating a more sustainable future through education.
Okay, thank you very much, Mr. of Ceremony, the Honorable our Dean of Faculty of Teaching Training and Education, Dr. Imam Sujadi, the Honorable Vice Dean of Academic and Research, Professor Nurma, and the Honorable our Chemistry Education Study Program, Head of Chemistry Education Study Program, Professor Elvi Susanti, and all of the participants. Assalamualaikum warahmatullahi wabarakatuh. Okay. Already with us here, Dr. Delaney. Thank you very much, Dr. Seamus, to accepting our invitation to become our keynote speaker at Chemistry and Chemistry Education Summer School. This is our routine agenda for once in 2 years. Before we start Dr. Seamus' sessions, I would like to read Dr. Seamus' curriculum vitae.
Bisa mundur ya tetap bayar 50.000.
Okay, Dr. Seamus, your lecturer in science and technology education and science, technology, environmental education discipline head, responsible for coordinating STE units across Deakin University's flood and physical campuses. He is the socio-ecological nexus, starts with Deakin Center for the Regenerating Futures and an elected member of Deakin Strategic Research Centers. Research for Professional Impact. He co-founded elements of sustainable chemistry, an interdisciplinary group with other Deakin science research. Dr. Seamus has worked as educators, researchers, and leaders in both Australia and Switzerland over his last 15 years. Dr. Seamus' research interests are in chemistry education, system thinking, teaching and learning approaches, sustainability education, and the incorporation of augmented and virtual reality into teaching and learning, and science education in out of schools or informal learning context. Serve on a number of boards, committee, and working groups that align with his research agenda, such as the Royal Australian Chemical Institute, Green and Sustainable Chemistry National Divisions, and the International Organization of Chemical Science in Development, where he is just been elected secretary from 2025. Dr. Seamus is also editor Oceania of the Journal Chemistry Teacher International. Dr. Seamus, for the academic positions, currently he is lecturer or research fellow at the University of Melbourne Graduate Schools of Education, Australia, from 2013 until 2014, and currently lecturer senior lecturer at Deakin University School of Education, Australia. And without further ado, let's welcome Dr. Seamus.
F7 untuk menonaktifkan keyboard.
Thank you for that very kind welcome. And I'm hoping my audio is okay. Just give me a thumbs up. I am sitting in a cafe in a hotel. I'm about to take a flight in about 3 hours, and it just started pouring rain. The heavens opened, and so hopefully it's not too loud in the background. If I'm coming through and you're smiling, I know it's going. So, I have to share. Thank you very much for that invitation, and thank you, Gigi, for the welcome and the opening to these 2 days. I had a look at the program. The 2 days look fantastic. Again, I'm sorry I wasn't able to join you, but I wish you all the best for these 2 days. And I recognized a few faces on the Zoom call, and I might be seeing some of you at the World Chemistry Congress, so you can tell me how the 2 days went there. Right, now let me just share I'm going to just share that. So hopefully that's coming through. Of course, when I do these, I always try and be as interactive as possible. So I will encourage you to, you can put things in the chat. You can ask questions along the way. I understand there will be questions at the end, but you're more than welcome to drop in and ask things along the way, because I'll keep the chat open. So why systems thinking in chemistry for Australia? As I already said, I'm involved with 2 projects that are funded by the IOCD, which is the International Organization of Chemical Sciences and Development. I'm currently the secretary. And the projects I'll be talking to today have mostly come out of the IUPAC Committee of Chemical Education and also the Interdivisional Committee of Green Chemistry and Sustainable Development. So it's a fantastic fit for what you have for 2 days, and I hope you get something out of it. I work in Australia. I live and work on the unceded lands of the Wurundjeri people. Wurundjeri people are a proud nation of people who live around the areas that you might know as Melbourne. Melbourne sometimes is referred to as Naarm. That's the traditional name for the area that I live. And I will be talking about indigenous science and chemistry a little bit later on, and get you to think about the lands, waters, and skies that you live, and to think about how you can be part of that, and making sure that what we're doing in the classroom is respectful and conducive with the local people. So as part of that, working with a website called AustraliansTogether.com.au, I've made a commitment to build a brighter future together. Oh, that rain is getting heavier. So just to put a context for why we talk about this. Maybe you've seen this study before. It's from Nature, published in 2020, and it was a study looking at how much man-made or anthropogenic mass there is in the world. And the study concluded that in about roughly 2020, the amount of anthropogenic mass, the amount of man-made mass, is now more or equal to the amount of biomass. Now that's the biomass for the entire Earth. So if you think about it, that's an astronomical amount. It's approaching 1.2 teratons of mass. And that shape of that graph, sometimes it's called the hockey stick graph. You see this shape of graph in many other scales and indicators of society. The life expectancy, population, same shape. Jonas Rockström of the Stockholm Museum Center has a TED Talk. It's thoroughly, if you haven't seen it, I strongly encourage you to watch it, where he shows this shape, this bend, sudden exponential increase is present in many other graphs, in socioeconomic trends, in Earth system trends. You see this shape again and again. It was Jonas Rockström at the Stockholm Museum Center who worked on this model called the planetary boundary frame.
Periksa
The Pacific Boundaries Framework,
apa itu?
with many others there, Will Steffen from Australia, sadly passed away a couple of years ago, Sarah Connell. It's a fascinating way of trying to encapsulate the ability to live within our means. And that study is currently concluding that in many of the scales that we might use to measure are we living within our means on Earth, we are most certainly not. Biodiversity is under extreme stress, climate change, as you no doubt are aware, use of land, we're using land in a way that is sustainable, access to fresh water and biogeochemical flows and many others. All right, so before we all get too doom and gloom though, you have to think about many of these anthropogenic masses, many of these masses were done for a reason, right? This is a systematic process, and is it the number one man-made material is concrete, and concrete gets used for all manner of things. We make about 25 billion tons of it every year, and that is increasing. So is concrete a good thing or a bad thing? This is the bit where I normally say, okay, so with the people next to you, ask them and talk with them. But I encourage you for the next 30 seconds maybe to put into the chat what do you think is a good way that concrete addresses sustainable development goals and maybe a bad way. So I'll stop talking for a minute and I encourage you to pitch me.
Jalur BDE kan dia ngerti yang gue mbak ketahuan jalur BDE di sini saya tak tahu sekali soal nomor iki reading di Indonesia yang ngajak di
Anita, current place for sustainable development.
saya nggak tahu kan ngantong ketahuan masih itu nggak terlalu diperiksa terus iki soalnya ini soal yang panjang struktur bisa nggak ngerti.
I'm not going to keep speaking until someone writes something in the chat.
Sustainable tadi. Yang baik, yang buruk.
Yep, please.
Amfibi rendang. Oh, metu mana amfibi kok cerita tentang kehidupan rendang. Reading, basic, bariku listening, terakhir structure. Soal amfibi ku tiap.
All right, fine. I'll keep going. I'll encourage you to say something else later on. Okay, well, what does concrete get used for? Concrete is predominantly used as infrastructure material. So I'll show you a picture of an infrastructure that I've seen recently. I was lucky enough to go to Mexico City. This is a photo taken on top of a cable car. You can see in the top right-hand corner there, there's a little cable car coming across. That is Mexico City has recently built a mix of cable cars that go across very dense regions of suburbs of out of Mexico City. That particular one that goes for about 11 kilometers. It's the longest cable car in the world. It takes about 40 minutes to go from one end to the other. And it goes across a really dense area. And look at all those buildings, all made from concrete. There are some tiny streets in between them, but the streets are too small for cars. So very, very dense populated area. Mexico City has a population of over 25 million people. And what are these cable cars for? They're to move people in and out of those suburbs. So if you think about it, concrete has a huge impact here on the quality of life, the living standards, clean water sanitation is used there to maintain clean water. So it's had a massive positive impact on these environments. You can also see there that not many of the houses are very tall. Mexico City has it's on a fault. It's on a fault line. I know in Indonesia you face many small. It's on a fault line, so it does get hit by earthquakes. There's been some very famous earthquakes that have completely destroyed Mexico City in the past. And too tall. So, because they know that they can build them very quickly with concrete. So, I would argue it's definitely had a positive impact for these people. These people then can move in and out, they can get into the city, they can access employment without having to put more cars on the road. So, yeah, it's definitely a positive. A negative, though, is it's really putting stress and strain on finite resources. Sand is a finite resource. That sounds ridiculous to say when you think about how much sand there is. But it's not just any old sand. It's the type of sand that they use for concrete production. Sometimes it's known as river sand. But basically it's sand that has a bit pointy and jagged edges. If you ever got your microscopes out there and you're wondering what to do with them, look at a few different types of sand under the microscope, and you'll notice that they are actually different. And it's the right sand can be very valuable. I come from Australia, as I said before, and Australia sells sand to Saudi Arabia. It sells sand to many countries because if Saudi Arabia just doesn't have the right type of sand. They have desert sand, obviously. Desert sand is round and it flows really well, but it doesn't work in concrete. So, the number one selling black market material. So, if you think of the black market, the number one selling material in the black market is sand. You know, it's not drugs. It's not. You know, it's sand. So, this is a material. It gets you to think about the material world aspect and how chemistry has a role. Responsibility to address some of these concerns in the material world. Chemistry has I would say at least now for 5 decades, a strong tradition of education research and envisaging how we understand the education that we use in the classroom through research. So summer schools like this are a great way of connecting with some of that education research. We've been doing that for years. It was Alex Johnson who set out this Johnson triplet, to think about why is chemistry difficult for students to understand. Well, we're asking students to juggle their understanding of chemistry on 3 levels. Symbolic level, we use a lot of language, we use a lot of terms, we use words in funny ways. Chemistry is one.
Kaya ako posting belajar TOEFL itu senang nasi nonton, gue kita rekam. Sinyalnya rapi kamu Telkomsel.
We expect students to manipulate materials, to scroll for that. So here, the Bente Shostrom and argue us to think about, well, actually, let's humanize.
Isi absen desi, Mbak. Nama Petri Priyatni dulu. Di itu, di Zoom.
Think about what are the life aspects, human aspects, and sometimes we call integrated learning. It should be tied to social considerations, economic considerations, environmental considerations. Not just saying humanize. We have to think about things when we humanize our people. After all, it was Vicente wrote a really fantastic article during COVID, and it argued us to think about that actually we let that happen. We let this untenable disconnect occur, where chemistry became this hodgepodge of disjointed series of facts. When we allowed it to become disconnected from the stories and the narratives of our students, of our communities, of our society. And so we are responsible for reconnecting with that. So I am here to talk about system thinking, and system thinking is I'll start with a definition.
Lagi pirang dino, lagi hari pertama absen, hari kedua
the complexity of the whole system.
Klik kanan, ini salin ora ya.
So what I mean by that is, let's embrace the complexity. chemistry is complex. Let's talk about the
Nek nggak iso
complexity. Let's
disalin,
understand what makes it
guru
complex.
iki ya.
But then
Apa
we'll do
link
that in a
absen
way
ini?
that helps us
Kepiye
understand
cara
the entire
kirim tiga?
system.
HP kira,
That will
iki
encourage
nang
us to
laptop, laptop
identify
bisa.
what are the intended uses of the system,
Klik titik
but also
tiga.
what are the unintended
Iya,
uses.
nggak bisa
And you'll
makanya
see a few of those.
lain. Nggak ada
With
makanya
Steve
fitur
Matlin,
salin.
also from the IOCD, we've recently published a chapter, well, actually it's not published yet, it's been pressed, it's coming out soon,
Apa tuh?
where we help define the chemical basis.
UNS Norma Watan.
And to do that, we started with
Link aku ngisi tadi aja lah, aku
the
bagi
simplest one that we have, the Earth.
link aku ngisi
Look at
di
the Earth.
aja.
Imagine you have
Gampang sih
the
saja
Earth,
ini.
and what are the boundaries of this system?
Piye?
Well,
Nah, mikirnya kayak salin kayak kena grup.
is that,
Kirim nang grup kita
all of the
mbak Ari mbak
mass
Lian
of
iso
that
absen.
system, for the most part,
Wah,
is a closed
Yeah.
sustain within that Earth.
Iki grup kita
Now, yes,
ciwi-ciwi
there's some
absen.
gases
Oh, wis ngisi
flow
kabeh
down
Mbak Arun loh.
to the atmosphere. And yes,
Absen.
occasionally there's meteorites that bring in mass. But it's nowhere near on a scale that
Oh, yeah.
measures.
Iya,
So,
CEC.
in essence, all the mass that's on our Earth is a closed system. But the energy most certainly is not. Energy is we have an open system when it comes to energy. Where do we get all of our
datang
energy
dia.
from? The sun. All that solar energy is picked up, here on Earth.
Aku tadi mau pakai hijau katanya pink ya.
Taken up as photocarbon converted to pictures. All that solar energy.
Hitam yang penting hitam katanya.
is material. We
Ada
use
ya,
it
aku bilang katanya
in
hitam.
there to get rental it. We use it in the system. And so that plays to that idea of material circularity. Here's some of those material narratives that we put into that chapter to talk about the sustainability of our material. You're mostly educated, so I thought I'll just give you an example of that. Often in the classroom,
Sudah 9 kali nih.
let's say upper elementary school or lower secondary school, we might get to the point where we start telling our students about the periodic
16 derajat.
things called the
Masuk
periodic
ke
table.
situ. Kemarin 30.
All the elements there on the periodic
Salah.
table. And maybe
Salah
with
kirim
that
salah.
activity, students can learn something about London elements. Represented on a poster or writing an essay about elements.
Masa
And here are the things that we might say are important.
saking nggak kering-kering jemuran di rumah.
We won't read aloud.
Itu, dia bawa ke sini dijemur.
But,
Panas
maybe
di sini di jendela.
in school where you've seen
Bisa sepatunya dijemur.
learn about all these things.
Aku juga
I'm not saying
penasaran dah.
they're not just
Makanya ada aja
doing.
tuh.
What are the students gaining? What's the learning outcome by students that memorizing all of these facts and figures? Instead, why don't we challenge our students to think about what that element is used for, why,
Cuci
if
nggak?
it's a finite resource, why is it
Dari satu ya, sampai
and then
satu.
when we do start to think about the fact that it is a finite, if we're thinking about how it's used, what are we doing? What are we addressing in chemical industry?
Saya mulai jam
What are we doing
9
in
ya Kak,
society?
sampai jam 12. Coba kasih
So
info
here's the
nggak
example of zinc.
deket-deket jam 12
Zinc
nggak
is
menuju.
an element that
Baru
we
jam 1
mine
Bu
and typically
Maya.
run out of in the next 30, 40 years. You're thinking, I'm not too worried about zinc. Well, you should be.
Nggak ada.
Zinc is used to galvanize metal surfaces, so it's predominantly used, about 3/4 of all zinc is used to provide road protection to
Aku rekam kok full versi rekamannya.
on uranium right now. So, if we did,
Chemistry,
the roof here
Apa?
will be rusting
Kimia
very
hijau.
quickly and so on.
green
So,
chemistry.
Right.
Dia mau hijau.
Now, the analogy that we use
Okay.
here is to say students have often heard of endangered animals. In a junior secondary classroom, maybe they learn about adaptations of animals. They might think about species. They might think about animals becoming endangered because of changes to ecosystems. Here, we're asking our students to think about changes. Make an awareness campaign for an element, an endangered element. Before I go too far, before you all jump on me, look, obviously it's an analogy. Elements are not becoming endangered. After all, we know exactly where they are. They're in e-waste. They're in material that's not recycled. We are the science of chemistry. We don't destroy matter. We just rearrange things. So the zinc is still there. It's just in a lot of waste material. So we just need to be more careful about how we use it. Because as that picture says, only about 30% of all things is recycled. 30% is quite high for most elements. Most elements are far less than 30%. But yeah, that means 70% could be a bit lucky. There's another one for tantalum. Tantalum is a very infinitesimally small amount, 40 milligrams approximately, is in our electronic devices. And yet it wouldn't work
Fotonya
out.
admin
So,
dari tadi ngecek suruh pakai background ini Pak, aku bagian admin dari Zoom ini.
Germany Democratic
Foto tadi foto Anindita ada bagi gambar bagi
but actually most of that stuff that's labelled as Rwanda has actually been smuggled across the border from the Democratic Republic of Congo. And these are two countries that only 2 weeks ago signed a peace pact that we don't know if it's going to hold. So this is a very war-torn region. Also in the news this week, because of things that are happening in our global trade right now, rare earth elements again. In our mobile phones we might have upwards of 17 of them, but normally not all 17, but they're mostly there as magnets. They're mostly there for diodes and such. Approximately 90% of them are processed in China, so it's very common. We might already in France we might talk about how they predominantly come from China. But actually, when we do say that, we need to be a little careful. They are predominantly processed in China. Increasingly, some of them are being sourced from other countries and taken to China. That's what Australia does. If Australia digs rare earth out of the ground, we put it on a boat, we send it to China for processing. This is increasingly happening in
Zoom-nya ini direkam full kok dari awal sampai akhir beberapa jam.
Myanmar has become a major player in the rare earth elements sourcing. So it gets dug out of the ground and shipped to China. However, this is predominantly happening illegally. This is for the vast part. This is all being done unofficially. Less scrupulous businessmen, shall we say, find people who will work in northern Myanmar, and what they do is chemistry. They take ammonium sulfate. Ammonium sulfate is known to be able to dissolve rare earth elements in clay minerals. So what they do is they dig a hole. Imagine like digging a little tiny hole and dig it down 10, 20 meters. They pump down bags and bags of ammonium sulfate, and that ammonium sulfate dissolves into the clay, and then they wait for liquid. So that they allow the liquid to come off, that is dissolved in these rare earth elements. Let it pool. They dig a massive hole and let that liquid sort of just collect in that pool, and then they wait for the water to evaporate, and they just wait and they wait and they wait. So here are 2 people sitting in that sludge, waiting for enough of the water to evaporate, and then they scoop off the sludge, and then they take that to China. All of this is done without any cooperation from the Miami government, and so what they do is this. Once they've got the sludge, they just move on to the next hole. Global Witness, which is an international organization, they did a report in 2022, and they looked at Google Earth and they looked at the satellite imagery, and they found over 2,700 of these holes in the mountains of northern Myanmar. That land now is completely unusable. It can never be used again for agricultural means. The water table is now contaminated. So this land has effectively become unlivable. Now, there weren't that many people living there to begin with. These are the mountainous regions of northern Myanmar. They're very, very small populations. But the people who live there can't live there anymore. So, I'm arguing this is not what we think we are doing when we buy
screenshot aku itu aku pindah ke laptop
Zoom today. We're talking from our laptops and our smartphones. I guarantee you, this has been happening now for over 10 years. There is rare earth elements in your smartphone, in your
Dr.
laptop
Nani
that
itu
have come from Northern Myanmar.
Smart
So we contribute in a way. We allow. We are spiritual to this system, and I don't like it. Systems
Tapi
thinking.
kok jauh ya Mas ya dengan Bu Citra ya?
They have a function. Think of some of the systems that you can think of. Think of our human bodies. All the reactions homeostasis and all the sort of process taking place in our body.
Orang
They
buka
have a
kamera
purpose, they
siku
have a
deh,
function.
tutup.
What was the purpose? What was the purpose and function of this system of exploiting the land and the labour of a war-torn country just to get the latest smartphone, the latest device? So that's my challenge. I'm asking chemistry education. So wake up. I don't think this is a sustainable process, and we do need to address it.
Ini latihan listening ini.
I think we are.
Kira
I think
listening,
we're in a small way.
aduh.
We are starting to turn the tide. The ISCD have a working group called Chemists for Sustainability, and they wrote a paper a couple of years ago where they tried to set out the basis for how chemistry can address human security. What is chemistry's role in
Fotonya buka
improving,
cam ya, foto
making sure
Anindita
that
itu.
people have a freedom from fear, freedom from want, freedom
Foto
to
tadi
live
ngirim
dignity.
ini suruh foto sama Mbak Arum
People
sama
like
Bu
Andy
Citra
Cannon
itu
and
buka
others,
ini, buka cam.
had
Kan
an
dia
expert
ada
group,
di
and they put
room,
together a
ada di
framework
Zoom.
around sustainable chemistry. This summer school is called Green Chemistry
Fotonya
for
kok nggak
Life.
ini? Itu foto buka tuh foto.
What we mean by green
Pakai
chemistry
ini
is
dia apa?
it's
Pakai
not
foto
completely understood
pakai
by everybody, but
foto
when you say
pakai
green
ini.
chemistry, people tend to know what
Earphone
you
dia,
mean.
kupingnya
Sustainable
putus.
chemistry is still got a ways to go, and so this is their attempt to define sustainable chemistry. The text in the middle, I don't worry about, but think about look around the outside.
Foto,
Equity and
Pucit.
justice,
Yang buka cam cuma foto
transparency,
tok.
circularity. These are words you wouldn't necessarily define with chemistry, and yet here we are saying that these are words that help us define what we mean by sustainable chemistry. I wanted to give let's say a more local example. Coconut oil. Coconut mangroves. Coconut has become a way that the cosmetic industry, pharmaceutical industries are finding a way of removing non-biodegradable fossil fuel-based material from.
Update.
Increasingly, people are
Foto, Patrick.
expecting to have their
Foto.
cream.
Lupa mau masuk nggak? Kita foto di Zoom. Screenshot. Masuk Zoom link itu.
So coconut oil.
Zoom yang ini.
They can do that.
Dikirim
I
foto.
recently gave a similar talk to this in the Philippines, and someone stood up and said,
Ikut-ikut aja.
there's a thousand uses,
Ratusan
1,000 uses for coconuts, and that's true. But think about what those 1,000 products came from one thing, coconut tree, right? So that's a very monoculture. Back to the Sustainable Development Goals. Again, I'm not in any way saying coconuts are bad. Coconuts are fantastic. We should be using more of them. But think about the impact that they will have on the Sustainable Development Goals. It's a monoculture, So if you build a massive mangrove, wash trees down, and you wait for those. It's you've developed a monoculture in that entire region.
Pak murid tapi ramai mahasiswa sudah pada anti. Di kursi duduk
You don't need to use too much fertilizer, pesticides for coconuts, but you use some. And so some of that inevitably is going to be overutilized, it's going to enter into water table and put stress on clean water.
Anduknya itu juga.
90% of all coconut plantations
Terus
are
sama Bu itu diganti sama Bu Dita diganti kalau mau minum aku ya bodoh aku dikei Mbak Nakwa dikei aku ya orang bodoh. Jadi nggak tak ambil dari Bu Dita dia ngasih aku.
But they will get a very, very small share of profits that will predominantly be favoured to much further up the value chain. So these people are not going to get much money from this. So
kami swasta, apa tidak?
We're benefiting from a system
tidak aman.
It's going to pay these people very poorly. We've seen this in many other industries, like the coffee industry and so on. Efforts have been the coffee industry.
Ya itu aku bilang hari ini.
Years now to make a better effort
tadi malam nggak ada yang tahu.
Gets back to the original plantation owners. The same needs to be done for coconuts. And these supply chains are very complex. There's a big opportunity here for greenwashing. If you see, go to your local chemist, your local pharmacist, and look at the way that they market some of their materials. They will market it as green, they'll market it as biodegradable, and then look at the products. there might be one thing in there that is biodegradable, and so 40 other things aren't. So, there's a big opportunity here for greenwashing. These are all problems we have solutions to. We know how to solve this problem. We know we can set up fair trade networks when it comes to coconut. We can encourage multi-crop. We can work with those farming communities, encourage them to use multi-crop processes. Put the mangroves a bit further apart, grow something else down the middle. Make use of the shade, to grow things that will grow well in the shade and so on. So these are all solvable problems. As a community, as a society, we just have to address them. Chemistry cannot excuse itself from at the table. It needs to be part of that solution. I was very lucky and fortunate enough to go to Monash University for this. It was a cosmetics expo. It happened in June. It was led by a fantastic individual, Lawrence Orlando and Zoe Porter. And Lawrence had them over 200 students. These are third-year pharmacy students and chemical engineering students. And they were put in a group of 5 or 6, and they had to make, over a semester, they were given the task of literally making 4 different cosmetic materials. So they had to make a moisturizer, a serum, sunscreen, and I think the fourth one they could choose whatever they wanted. So they were given time in the lab. I was invited there. Several of us were. We became the assessors. They had to give it to us, tell us about their products. But they would, when they did tell us about their products, they were incorporating the idea about what was sustainable about it, what was important. And so when you look at it, you can see the little maps they were doing there. They were making these little socket maps. So I was there. I met them all earlier, the students earlier in the semester, and I gave them a talk similar to this one, and then I challenged them to use socket to represent how their product were sustainable. And so yes, they use this thing called a systems oriented concept mapping extension, or a SOCME. We've had these in literature now for the last year, and I'm going to show you a few examples. To get there, what have we been doing? The software program's only been out for 2 years now, so we're doing. We were making these. We started. This is the first one we made back in 2019, working with a teacher in New South Wales, Andrew. Andrew, Madeline, and I, we published a paper about this where we had these systems maps. We challenged the students to put a chemical reaction in the middle. And then Andrew had them, okay, what are all the ins and outs of that chemical reaction? What are all the masses that you need, for that? So this is ammonia, making ammonia. So how do you make ammonia? You make it from nitrogen. Where does the nitrogen come from? Oh, it comes from air. Where does the hydrogen come from? Oh, okay, well, predominantly comes from fossil fuels. Interesting. What is ammonia used for? Very rarely do we use ammonia as ammonia. It gets turned into something else. What are the intended uses of ammonia? Predominantly fertilizers. The vast majority of ammonia is turned into ammonium-based fertilizers, and those fertilizers are used to feed our population. So there you go. That's how we went from 1 billion to 9 billion people in little over a century, feeding those people with a fertilizer made from air. But just think about that for a second. We feed people with air, but we also feed people with fossil fuels. Because that hydrogen is still today predominantly sourced from fossil fuels. What are some other things that ammonia is used for? Yes, you can use it to make vinyl-based plastics. Obviously, as ammonium-based cleaners, explosives. That's all of Nobel's work. So it's getting you to think about it. And Andrew challenged students to colour in their map. And so green is good. Green is it addresses the sustainable development goals. Red is it's a negative impact on the sustainable development goals. But yellow is like, look, it's complex. I can't. There's ways that it positively addresses sustainable goals, and there are ways that it negatively addresses sustainable goals. And I think that's a good result. A student who is being challenged to think about how chemistry has both positive and negative impacts. I would call that the central learning outcome of chemistry. I said Tom Holmes' name. The central learning outcome of it's pedagogically essential that we do that. After that experience, we ran a professional learning network for a year. We had a group of teachers. We followed this for a year. We really followed them. We put them together. Hey, what do you want to do? They were great. They went off and did things, and they wanted to do these maps in their own class. This is an example of a student doing a map at the start of the year. This is a typical concept map you might see. They put like a big central node, and then just things coming off that node. Very classic concept map. This is the same student a few months later, and now obviously they're doing the colours because they were told to, but look at all the arrows. They're much more. There's arrows connecting different things. They loop back around. So this student is now demonstrating indirect or moderated linkage. The student is thinking about multi-component causal reasoning. They're not going to call it multi-component causal reasoning, but they're going to think, for C to happen, both A and B must happen. And if B is happening a lot, that means D is not happening as much. So they're thinking about the circularity of these processes. They're much more aware of impacts, individual impacts within a system. But that's good. In the same book that I'll tell you about in a second, another chapter that we've written is to make one of these SOCMEs on lithium. Mary Kay Ogle and Scott Donnelly and I, we met over the course of a year, and we wrote this chapter thinking about all the ways that lithium. So we thought about the map. We thought about where do you get your lithium from? Lithium, if you're listening at home, lithium, majority of the world's lithium has come from Australia. One mine in Australia, Greenbushes mine out in Western Australia. So, yeah. What is it used for? What are the intended uses for lithium? Obviously, it's batteries, it's smartphones, it's e-cigarettes, it's electric cars, it's storage, energy storage, all that sort of thing. But then, what is it? It's inevitably going to go into waste. So, how do we waste? What's the disposal process? But then we extended to think about what are the environmental subsystems? How is lithium tied to the land, the water, the atmosphere? What are the social and political considerations of getting all that lithium out of the ground, turning it into our batteries and our electric cars? And so what are the social and political requirements? What are the ethical considerations? The economic considerations, national sovereignty, all these sort of aspects you need to think about. And so when you look at that entire thing, as I said, that we would argue that is telling you everything you should be thinking about lithium in all those different subsystems. And every single time there's an arrow that jumps from one subsystem to another, that is it's demonstrating boundary crossing, a subsystem having an impact on another subsystem. I cannot stress this enough. You would never do that in one sitting. The intention is never to make one of these in one go. You might come back to it every now and then, and you might add to it, and you might work with the students. It might become a way that's, say, a classroom, consolidate all their knowledge. Maybe you encourage students to build it up over time. Over a unit of work, they might come back and add things to it as they go. But really, it's an ability to collate the entire understanding about a topic. But it's got ethics in there, it's got geopolitics in there, it's got end-of-life ramifications. It does come across a bit chaotic. We do start to sound a bit crackpot and crazy, but it's complex. So it's a fine line. You're walking a fine line here when you make these. You want the students to embrace the complexity, but not find the complexity overwhelming. So what can we do? We can stick to simple ones. This is a teacher, NASA. NASA's crew is amazing. I don't have to run many of these workshops now. NASA will go to Science Teacher Association meetings, and he'll run the workshops. NASA's been a real ally, and telling other teachers about this. He's been an early adopter of this. And NASA will, he'll do it, here's an example of a student doing it about Australian ore. He'll also find other ways of having students do it. That one there on the top right, you can't see because it's quite small, but actually it's a student planning and experiments. Here in Victoria, in year 11, year 12, they have to do, one of the major assignments that they have to do and report their results to the government is they have to design an extended experimental investigation. So here is a student using systems mapping to visualize and design their experiment so they know that they're addressing the right things. Last year in ICCE in Thailand, and maybe some of you were there, we ran a workshop with Peter and Leisha and David, Vicente, the five of us. We went through this and we gave people in the room a chance to play with SOCMID. Here's a few of the examples. There was a fantastic German individual he did one around colours of hydrogen. I'm thinking, conscious of time, I won't go into colours of hydrogen, but thinking about all the ways that, yes, hydrogen doesn't have a colour, but the colours of hydrogen becomes a way we're talking about where the hydrogen is ultimately sourced from, and so how sustainable, how renewable that is. We're starting to gather more evidence that this is a good thing. It's something that really just started in 2018, 2019. There isn't a huge baseline of data. So we're starting to gather that evidence. When we do speak to teachers, they like the idea that it has students researching more broadly. They're having to think a bit further about the topics and the content that they're learning about. It's when we ask students really like that idea that, they're being pushed to think beyond just the chemical reaction. Think back to that one I showed you before, with nitrogen plus hydrogen goes to ammonia. They're having to think all the other ways about this reaction. So this is a student, telling us, and this is really affirming to us that, it's not just surface level understanding. They're being challenged to think about the depth and the breadth of the chemical phenomenon. It's not just us. There's many other studies. Lisa's Sosa just finished her PhD, and she's got a couple of papers out there where, both educators and students tell us that, they feel like it's enhancing their learning, that it's embracing interdisciplinary concepts, it's engaging, it's motivating. It pushes them to think beyond just the content that's in their course. Look, it's a way of, getting them to think about their futures, about, being job ready, skills development. What are the key skills that industry and jobs in the future are going to be looking for? One of those, not the only one, but one of those is being able to be consistent think. So they like the idea that it provides personal and social relevance. And I think the last one is very important. It's improving the image of chemistry. Chemistry doesn't have a great image. I'm preaching to the converted. We all think it does. We all know that in the past chemistry doesn't have a great image, but it's a way that we can own some of the mistakes of the past in chemistry and show that we've embraced and we're learning from those, and we're designing chemical industry and chemical engineering to do better, to be sustainable. So it's improving our image. It's a good mark. We're completely aware that this is not, we won't hide from it. We know this is difficult. So this is a group of people, the five of us meet occasionally, and we're also busy, so we don't meet as often as we want, but, acknowledging and overcoming what are the challenges that educators face in implementing systems thinking. We know that there's a lot of institutional inertia. You get out, you pick up any curriculum around the world, and it won't have written down in the top point somewhere systems thinking, but it'll be there, but it'll be there implicitly. Students have to learn about biogeochemical philosophy. Students have to learn about sustainable principles. Students have to learn about, they'll be doing those things, but now thinking becomes a way of connecting with that context. So So yeah, there is some ways we can overcome institutional inertia, and we just need to develop the confidence and the motivation to do that. So that's a way. These are things that we're trying to overcome. One way that we're doing that now is since last year, Vicente and Alicia were authors on this article, but really it was the IUPAC System Thinking in Chemistry for Sustainability group. We were meeting over the course of 2-3 years, constantly coming back to how do we support educators, how do we support educators, students. So the culmination of that work was this framework. So now when we go out and we give these talks and we give these workshops, this is largely the framework that we try and support people to use. So I don't have time to go through it all. I'll pick little bits to talk about. But as you can see, it's about contextualizing and defining the work, setting the learning outcomes for your students, and then implementing them, mapping it out, visualizing, zooming in, what's important, zooming out, seeing, and making for the most part, it's about using those visualizations to visualize zooming in and looking at those individual components. What is the chemistry that we're learning? What's happening on a submicron level? That's the system. What's happening on the macro level? That's the system. So getting in and figuring out what are the ways that the chemistry interact with us. And then zooming out, stepping back and saying, recognizing that when you have that system in place and the interaction between the components of that system, we see the behaviors. We don't see the components. What we see is we see the behaviors of those materials. So now we start to see the system behaviors. We start to see the system effects. We start to see how, that little simple chemistry on that submicro level, on the macro level, what is the impact that it has on society, on the economy, on the environment. So that's us connecting, incorporating the human story into that chemistry. Some of the language that we're encouraging people to use is here. So these words don't come out of thin air. They come from people like Mary Kay Walton, who developed really Mary Kay went deep dive into 40, 50 years of systematic individual and other disciplines, come to a set of key characteristics or a set of ways that we can use some of the terminology in chemistry that you'd expect to see in system thinking. So, talking about system composition, identifying individual components, what are the boundaries of the system, identifying the structure of the system. And that structure could be just making connections between 2 or 3 components, understanding the nature of that relationship, seeing how those relationships come together to be one big map, one big structure. Once you've got that in place, you can start to go, okay, what are the behaviors of this system? What are the behaviors that emerge out of that system when you start to interact and engage and observe things? What do you notice? What do you see? They're the behaviors that are due to the relationships and the interconnections between those components. And then lastly, system effects. Little difference between system behavior. But now when you look at the system as a whole, you think about the holistic nature of that system, you start to see what are the effects that system has on other systems. What are the intended impacts of that system, but also what are some of the unintended consequences of that system. So they become system effects. I will now try to give you an example of that. I'm going to zoom out and look at some of those system components, structure, behavior, and effect. I'm not going to do it on a particular chemistry phenomenon. I thought I was going to challenge you to think about something a little more broadly that is a summer school. I'm going to challenge you to think about, I'm going to zoom out on a chemistry education system and think about, because we're a component, we're in that chemical education system. So let's look at that. I'm speaking to Indonesian, predominantly Indonesian cohort today, so maybe you know of this and Tuni, I think you're in the audience. You've been fantastic for doing this global survey that we've conducted. Istog, Madeline, Sidwan, and I, our Fred Dr. Austrani, we've been doing or have done a global survey of chemistry teachers. In the end, we got about responses from about 10,500 teachers from 57 countries, 37 languages, and including one of those in Asia. And look, I just wanted to show you, so these are our components. This is one component in our chemistry education system, the school teachers, and so they're a component. And there you go, the Indonesian response largely matches the global response. So when we do get some global data, it will support and inform on chemistry education in the region. And we ask them questions like, what are some of the things that prevent them from doing more practical activities? Now, these are practical activities in green sustainable chemistry practical activities. But, we can extend it further to think about these are factors that teachers tell us about that are putting a barrier to them doing things in the classroom. And so here is the structures that the interrelationships that they have. They have a relationship with the curriculum. Curriculum is another component, and that has a relationship with the teachers. So that is an example of the structure. Their motivation, their commitment, the time that they have to implement that curriculum. These are all things that put a barrier to part of that structure.
Pas mau mesen nasi, Pak Muntalib, ya dihitung,
Just briefly then,
verifikasi,
look
kata
at
Pak
that,
Muntalib
the
gitu.
ones that stand
Ya
out.
udah tambahin 3
Indonesian
Pak ya,
teachers tend to
25.
say
Akhirnya kelebihan, lebih 3, 3
they
juta
don't
kasihlah
feel
ke yang
time
di lab, Pak
such a
Yudi
barrier.
sama ini. Pokoknya yang ada dosen di situ ya.
They're not saying they have enough time,
Aku
but
kan sering pasti
they're not
bagikan,
saying
kalau aku
that they're
dikasih aku
concerned
terima,
about
kalau enggak
time
ya sudah,
compared
karena
to
aku
say the
enggak dalam
global
makan nasi
average.
kan.
Same with
Nah ini tuh
curriculum,
mbaknya
they're
sama
constrained,
Nana.
that's really good to see.
Oh ya dapat ya
One
sudah,
thing that they
aku
are
terima karena
highlighting is
kalau
lack
dapat,
of
kalau enggak aku enggak minta kan aku diam.
Now, this is about
Itu kan
productivity.
untuk kamu
The
berdua, aku dikasih
a
sekantong
lack
gitu
of
kan,
resource
bawa dia bagi-bagi ke semua peserta itu kan.
to do the
Kamu
productivity
sama, terus
that
aku
they get
diam
in the
aja,
classroom.
aku diam aja kalau
That
aku
is a
kan
behavior,
bantu
that
ngambil
is
kan dari
a structure,
bantu
lack of
ngambil bayar segala macam juga, kalau
So
aku
that
dikasih
becomes a
aja
way
kalau enggak ya sudah aku
we
diam
think
kan,
about
kasihkan
this
semua ke dia,
behavior
aku bantu
system.
bagi-bagi selesai. Ini lebihnya banyak pada dia ini
How to,
ibu
if they
mbaknya
want
sama
to
Mbak
do
Nana,
more
dia
green
nggak tahu
chemistry,
nama
if they want to
jadi
do
itu mbaknya sama
more
Nana.
sustainable chemistry
Terus
practical
itu
activities,
dia tahu nama
where
PT
do
aku
they
tuh
get
karena
them from?
pas di mobil itu
And
mbaknya
then
ngomongin cowok-cowok
Indonesian
factory
teachers
itu,
are
awalnya dia
predominantly
mau
learning
jelasin
from
mbak
other
nggak
teachers
tahu kan pas itu. Jadi
far
aku diam
more
aja,
than the
nggak
global
dikasih
average.
snack
So
gitu dia,
they're relying
nggak
on word
dikasih
of
nasi,
mouth,
aku
they're
diam
relying on
aja.
speaking to other people.
Aku diam
Yes,
aja kan.
they
Aku
are
diam nggak
coming to
dikasih.
professional
Terus pas
development.
waktu ini
It's
untuk
another
ini
big
ya,
one for them.
2 ya
They're
jatahnya
coming to
dua,
things
yang lain
like this. They're
dibagikan ke
coming to
dosen.
teacher
Dosen
associations.
dibagi.
So subject associations, government organisations that run professional learning
Wah parah
have a
sinyalnya ya.
strong. They're a very
Angel ya.
component
Angel.
in supporting supporting teachers to implement the curriculum. And so that is the behaviour. Professional organisations, subject associations, providing professional education to teachers. That is an example of a system behaviour. That relationship that those associations have with the teachers, that leads to teachers developing disciplinary knowledge, pedagogical knowledge. So that's an important behaviour that we need to nurture. In Australia, in Victoria, how are we doing that right now? One example of that is, until very recently, I was the president of the Chemistry Education Association. We have over 1,000 chemistry teachers as members in Victoria, and we run PD. We get teachers to come in. They turn up. They learn the activities. They learn the experiments, and so that's the way that we are contributing to that behaviour. And I did say at the start, I mentioned briefly that lithium comes predominantly from Australia. 55% of all the lithium that's ever turned up in a device, in a car, came from Australia. We dug it out of the ground though. We don't process it. We dig it out of the ground, we stick it on a boat, and we send it to China and they process it. I understand that's a different story in Indonesia. For instance, nickel. Indonesia is starting to have a strong influence on, good for you, having a strong influence on the nickel industry, controlling the nickel industry and doing it in a way that they're increasing the value chain. They're not just digging out of the ground, they're processing, turning it into something that has a high value. But, that has an impact on the environment, it has an impact on local communities. So So that's the part that we still need to work on. But, we're getting better at it. But I would argue that I did say I'd come back to this.
Boxnya merah apa itu Mbak?
Many of the
Itu ya.
benefits from that process, taking lithium out of the ground, they were not part of. They were not part of a system effect. So look at that. Here's a system. Here's our environmental system. This is our human system. Here's our chemical system. And I've circled two relationships there. I've circled two interconnections there. The human connection between the earth and how the production of chemicals is having an impact on the earth as well. Many of our indigenous communities, our local communities who live and the connection they have with the land, the water, the skies in these areas, they've become disconnected. The local indigenous people here in Australia, we've had local indigenous people, 65, 70,000 people, 70,000 years living on these lands, over 400 languages. It's not the same number of communities, cultures, unique in their own ways. I live on Wurundjeri land, with many others, and these people are telling us, when they are given a voice, they tell us their connection, that relationship that they have with the land, the waters, and the skies is being put under stress. They are being marginalised. And so that is part of that system. When you zoom out and you look holistically at the system of lithium, of the chemical process of lithium, you start to realise that a system effect, an unintended consequence of that, is breaking the connection that indigenous cultures have with those lands. I've listed it there as an unintended consequence. I'm very aware that quite possibly it was an intended consequence. We talk about the I'm white. I'm not indigenous. My name, Seamus, comes from Ireland. I go back 150 years. You find my ancestors in Ireland. So one could argue that colonisation was a process, an intended process to break that connection that these local people have with the lands. So I get you to think about in your own country. Would you agree that some of your local indigenous communities have had their connection to the land, the water, the skies put under stress and strain? And is chemistry part of that? If chemistry is part of the problem, chemistry can be part of the solution. And so one thing that we're doing, this is an ongoing project, looking for funding, so we'll keep pushing. Amazing people like Africa, Angela Zeibel, who are saying to us that we need to decolonize our curriculum. We need to think about how we critically reflect on how our curriculum, the chemistry that students learn in the classroom, is itself a colonial construct, is deliberately written in a way to marginalise and exclude Indigenous knowledges. And so we need to own that. As non-Indigenous educators, we need to challenge ourselves to recognise the diverse knowledge system that we have. Indigenous peoples in Australia were the first system thinkers in Australia. So reflect on how they were thinkers and reflect on how colonisation prioritised certain parts of knowledge and how we can address that. And so, I'm just going to highlight a couple. Here in Australia, we've got the Australian Council of Deans of Science that have provided resources that have fantastic material that could do that. The First Nations Australian Science Curriculum Development Kit is out. Got some fantastic material in there that, yes, it's about First Nations, but you could use that to work with a local Indigenous community in your country to think about how you embed their knowledge system into what you do. That's enough about decolonisation. I'm going to end with two things. How about industry? We have a role and responsibility to embrace systems thinking in chemical industry. Chemical industry actually doing this pretty well. Some chemical industries would say we do systems thinking. They look at it strangely. They say, why are you using your school system? Why high school, undergraduate, postgraduate, why aren't you teaching more systems thinking? Because when they come to us, we expect them to be systems thinkers, and they're not. And so then it falls under us to do that. So wouldn't it be great if we could say to industry, hey, these are the type of people that we are producing, and look at the thinking that they have. This was a study done by Emi Virio during her PhD, where she interviewed industry people, and she sat next to them, and she was making this map as she was listening to what they were saying. This is an example of someone who works in the paper industry and getting him to think about how in the paper industry they try and use waste material and turn that waste cellulose into other material that can be used for other material processes. So encapsulating how industry, not all industry, but how industry is doing great connection, and then what we could learn from that experience. To that end, there is a new our Systems Thinking in Chemistry for Sustainable project is wrapping up. It's our last year. And so many of us have moved into the next project. It just started, it was announced a couple of weeks ago at the World Chemistry Congress, and so you'll be hearing more about it. Jane Kissinger, Steve Matlin, Peter Mahaffey, myself, and many other industry people are now part of that project. It's called Systems Thinking, Sustainability and Chemical Industry, or SISTI. And what they're currently doing is they're writing a white paper. Stephen is leading a team of over 10 industry partners to write a white paper that is going to set out policies in how chemical industries could strengthen their connection to systems thinking. And I'll be part of the team that will take that white paper and develop a series of case studies that can be used in the classroom. So I'm really looking forward to that. I would argue that in 2019, we were behind. You know, Peter Mahaffey stood up at ICC in 2018, gave a plenary about systems thinking and said, we should do systems thinking. Because we weren't, the IOCD put out a paper in 2015 and introduced the idea of one world chemistry. And that, you know, we were behind. There was a paucity of literature that showed that we were doing systems thinking in chemistry. You're far more likely to find systems thinking literature in biology, in environmental science, in earth systems, in engineering. So we had to catch up. So challenge accepted. We decided we're going to do this. And you will now find resources, educational resources, teaching modules, online communities through many of these organizations, the ACS, the Journal Chemed, especially in 2019. The Beyond That I now have a thing called the Green Chemistry Teaching and Learning Community, or GCTLT. Anyone in the world can join. It's free. We join an online community. I definitely urge you to check it out. I completely own that that's a fairly westernized list there. I'm still showing my own colonial tendencies. I'm sure there are many other non-Western examples of organizations that are doing this. We'd love to hear from you. We'd love to hear more of these, how it's been done around the rest of the world. And I'll give you an example of how you could do that. No, not that. I'm going to do that one. So what I'm going to do, I'll skip to this slide. I need to reshare. So I'm going to finish with asking you to consider 2 special issues and a book. We do have a special. This is hot off the press. I think you're the second people to hear about this. There'll be a new systems thinking special issue. It's going to be announced at IUPAC, but you're getting a preview. We have funding to publish a new special issue in Chemistry Teacher International, which is IUPAC's education journal. We're looking for 10 to 15 examples of authentic, actually done in the classroom, actually done in the teacher education space, systems thinking approaches. Wouldn't it be fantastic if we had more than 15? But, you know, we're encouraging you to submit a proposal that you have. We're not after theoretical stuff. We want actual stuff. We want you to show us something that you've done and inspire people around the world to do something similar. That, after all, is the mission of Chemistry Teacher International. I'm one of the editors. I know this. Abstracts to be due at the end of the year in November. If you're chosen to go to a full manuscript, it'll be due in May, and it will publish them as they're accepted in CTI, but if the whole thing will be published as an issue later in the year, but they'll be accepted as they'll be published as they're accepted. We do hope to completely waive the APC, the processing charges for that. CTI put up the prices later than this, so the fact that we managed to get a waiver is impressive. Thank you to the IEPAC Committee of Communication, the IEPAC Interdivisional Committee of Green Chemistry and Sustainable Development, and the IOCD. We're throwing in some money to make sure that we can publish these with a 100% waiver. If system thinking is not your thing, but contemporary chemistry is, there is another special issue that's been announced in ISTOC's journal, in the Centre of Education Policy Studies journal. I strongly encourage you to check that out as well. It's got a theme, chemical education in contemporary global society. There's dozens of these things. So you can really, as long as it's contemporary, that's one that we can think with well. Similar thing, abstract published. And there is a book. There's a book coming out in December. This amazing editorial team approached us. I'm a co-author on 2 chapters. There's 10 chapters in the book. And the editors challenged us to come up with teaching activities. Some of the authors, that was a challenge, but I'm from education, so I was fine with it. The 2 examples that I showed you, the endangered elements poster and the lithium software are in that book. But when it comes out, it'll come out in December, and I really encourage you to, because I think this is going to be a book that really pushes forward chemistry for sustainable development. Thank you so much. Thank you to University for Merit for this fantastic invitation. Fantastic to see some fresh faces, and I'm more than happy to hang around for a while and make some questions.
Okay, thank you very much, Dr. Seamus. Dr. Seamus has explained and awakened us all to the fact that many of today's world's problems are related to chemistry. This includes the duality of a function and the disadvantages of concrete and science, as well as other issues related to the fragility of the words. Furthermore, chemistry is a complex and requires a holistic, complex thinking to solve problems with all the consequences. It's called system thinking. So system thinking has a purpose and functions. Manuel Stokesly is a tool that enhances and supports interdisciplinary thinking and global awareness, providing personal, social, and professional relevance. So, for all of the participants here, can ask directly to Dr. Seamus. And we also already have one question here in the chat box, Dr. Seamus, from Dr. Parsi. Regarding the system thinking approach in chemistry education, can we mention that the approach actually related to cognitive ability as the origin of the system thinking definition? But according to the system thinking framework, it can perhaps be connected to the student's values and actions. So the question is, it is possible to develop the integrated assessment tools following the system thinking sequences.
Thank you, see, and it's good to see you again. I'm going to email you after this. Yeah, absolutely. Again, in the time that I had today, I wanted to show you many things. I did gloss over perhaps some of the ways that you might focus and define on the learning outcomes of as a sequence. Part of that process would be to, as I said, I skipped over that context, focus, define, design aspect to the framework. Definitely a part of that is to first of all think about what the context you're going to look at, but then you very quickly move into defining the learning outcomes, and those learning outcomes are going to be more explicitly connected to the skills and the cognitive abilities and the competencies that you're looking for. That's just good old education 101, but you're going to think about what the parts of the system that you're interested to look at, and then you're gonna phrase those as learning outcomes. And so yeah, I do strongly encourage you to. I know you're aware of this because I've seen some of your stuff. To think about the skills, how you might define some of those skills. You know, Mary Kay talks about the five characteristics. Alicia and we also talk about Alicia had in her PhD, she had 11 skills. You know, but just think about when you look at those skills and competencies, they become ways of, you know, how a student might represent or demonstrate. And so that becomes the cognitive thing. That becomes the thing that, as an educator, you're looking for. But to your question about zooming out and thinking about the values, yeah, look, I've focused on talking about having students engage with the value and the role and responsibility of chemistry today, but that will play out by the skills and the competencies that you define as learning outcomes in the sequence. So yeah, it's you know, it's both. I get to your question that as good educators, you are going to set out what the learning outcomes are. You're going to base that on individual. Don't get too reductionist, but you're going to do that on individual skills and competencies that you're looking for, and then that is going to play out. You know, students will have engagement that way. But yeah, very good question. I can see another question here. Oh, yeah, okay, yes, fantastic. Wait, so yeah, this is a good one. So I can do this. So you want me to go through how about, okay, I can do pollen. Let's do pollen. So how do you, we're making plastics. Let's just make a simple plastic. So I'm going to contextualize this. So I'm going to contextualize this in the sense that I want students to learn about how plastics have become embedded, they're just ubiquitous through their everyday lives. Because sometimes students think, oh, I can avoid plastic. In Australia right now, we're having a plastic-free month. And I just laugh out loud. I'm like, how could you have a plastic-free month? But anyway, so let's do that. So our context is having students think about that. So what's the chemistry we're going to look at? We're going to get into, let's pick a polymer. Let's do polyethylene. Where's the ethane come from? What's the monomer? Ethane. Where does the ethane come from? Ethane. Where does the ethane come from? What's the fuel? The distillation. So I'm gonna walk students through, you know, polymerization and addition polymerization. That's going to be some of the chemistry that I want to focus on. So I'm gonna do that. Then I'm gonna maybe have some practical experiments, and maybe I'm gonna have, well, we know what to do. We could recycle this plastics. So I'm going to get out a few different types of plastics, and I'm going to have the students test the properties of these plastics. And they're going to notice some of them char and burn, some of them they go black and so they can't be recycled. Some of them are going to melt and can be remolded. So they're going to think about the properties of those materials, and they're going to relate that to. But then they're going to think about, oh, okay, so all of that material that couldn't be recycled was burnt and charred. Chemical properties, the interlinkages in those polymers made that material very hard to recycle. Is that the plastic that turns up in our environment, in our system? So I'm going to challenge them to zoom out. I'm going to challenge them to go out further and consider how that simple chemical reaction, the monomer to a polymer to make polyethylene, how that plastic that couldn't be recycled has started to cross the boundaries of that community and is entering into the land systems, entering into the water systems. And so it's having an impact, it's having a system behaviors in those environments. So then I can bring in context like ocean plastic. I can bring in context of ocean acidification if I want to go that way, but you know, let's stick to ocean plastics. And so now a student is suddenly realizing that that simple reaction of ethane to polyethylene, how that plays out in the community, how that plays out in where plastic ends up in our land, our waters, our skies. And they start to wonder, why does 1% of all plastic get recycled? What happens to the other 99%? Why is there so much plastic? They think of plastic bottles. That's the smallest amount of plastic. Our computers have plastic. Our houses have plastic. We use it as a very common insulating material. We put plastic tinting on windows to improve insulation. Once you put a tint on a glass window, that glass can no longer be recycled. So there's all these sort of things that you could really do and get students to make recognition. I feel like that's a really long answer to that question, but it's a complex issue. You have to look at many different things and aspects. But that's just one way you can do that. Is that the same question? No? Okay, I did that one.
Okay, the next question may be from Dr. Lina.
Yes, thank you, Dr. Ari, for the time. Dr. Simus, thank you so much for your interesting talk. And I have some questions regarding this. So first of all, you said that it cannot be done within one set correct? Maybe one class. And how you suggest we can do to have this identifications on how the system thinking of the students if we don't have really a long time for the class. And then the second is regarding to Dr. Asih questions about the cognitive aspect. How can we classify it based on the students' respond or students' answers on the certain topics? I mean, like how we can classify if they have good system thinking or higher system thinking, and how we can overcome or at least strategies to increase the lower or the mediocre student with have good system thinking. And the third one is how we can we simplify the system thinking process because I think the system thinking can be influenced by someone's
Tapi
experience
provinsi itu nggak tentu,
and
satu provinsi hanya ada di ibu kota, ada yang di pelosok,
knowledge.
ada yang itu nggak
If
tahu.
someone love to read or someone love to
Iya.
not like to read, and
Dosen
maybe
juga
they don't
itu
have
kurang
really
ya, pas
high
penempatan.
system thinking because you connect all those aspects like social and then
Kan dia nggak sanggup ya
chemistry
dengan
and then
tuntutan.
politics and other things. That's all my questions. Thank you.
All right, I'll do
Bisa
my best.
kayaknya
Remember,
karena
let's
suara
go back
Ed
to
itu
question one.
bukan
Might
PNS,
be two and
apa
three,
itu namanya
but let's do
P3K
question one.
gitu.
Yeah, look, the reason why I said you couldn't do that
Oh
in one
nggak harus
lesson,
terus
what I meant
harus
was
masuk
that's
asrama
really
full
complicated.
ngajarnya nggak boleh
What I did
keluar,
that
ini
had like the
bener
8 or 10
terikat,
different subjects.
nggak bisa kayak kita kan
Yeah, I
kok
wouldn't
guru
do
kan
that.
nggak ngajar udah kan nggak datang nggak saya kan gitu kok itu harus full terikat semua kegiatan
Definitely
Kemensos.
you could do
Oleh Kemensos itu.
you could do I mean, we regularly do a concept map in a lesson, don't we?
Yes.
So you could do it in a lesson, but you might not expect the student to go to that level of detail in one lesson.
Okay.
So what I meant by that is definitely I would encourage students to like the ones that we used to do with Andrew and we still do. It's like put a chemical reaction in the middle. Tell me everything you know about the mass that goes in, and tell me everything you know about the mass spectrum of what it's used. That could definitely be on the lesson. So that is like that idea about and so you don't do any
Kalau
social,
putih kan tuh ya nomor kutipan
maybe even
kode
environment.
subkode
You just keep it to the idea about mass and energy.
permasalahan narasinya
What mass in, mass out, energy in, energy out. That could be a way of a nice, simple
baru
start
ada
to
kode tema.
thinking about these chemical reactions, not as equations, not as just, symbolic language on a page, but starting to think about them as a system. That'd be the simplest thing to do at the start. So I think that's a nice, simple way to start, which is a bit of an answer to your third question. I would also, as to the cognitive point, and how do you differentiate low, medium, and high ability? Absolutely. There's an aspect here of, we in Victoria we have
Tapi
in our teaching standards we have the know your students, know how your students learn. What they learn, the curriculum, but you know how they learn. You think about how they normally represent their answers, what are their misconceptions, what are their alternative conceptions about chemistry. One of the alternative conceptions they will have about chemistry is that it's not a system, that it's not, So I think overcoming that alternative perception at the start will be a way that you get some of our lower middle
aja yang
students
panjang,
who
enak, betah dia di situ
see
berarti.
these as just symbols on a page, they just see it as NH3, but they don't think about what is NH3, what
Iya,
is it
bawa
used for.
keluarga, bawa
I think that could be a simple way to get a load
ngaji
of
terus
reading.
mandir-mandir ya.
From medium to high, I think that is you're pushing students to get away from a very linear approach to this. Think of phrase you might hear a lot now. Well, a lot is strong. You'll hear it more now is circular content. And having students, a chemistry student, realize that. So yes, maybe this is a student who already thinks about ammonia gets used to make fertilizer. So they're thinking but they're still thinking quite linear. They're thinking reactants
Iya,
go to
lebaran nggak mungkin
products.
nggak
I
pulang.
use that product, it goes to waste. Very linear thinking. A high ability system thinking students will start to think about the circularity. And so when they draw their visualizations, they make their maps. There'll be arrows that loop back around. There'll be arrows that go in two different directions to form two different things. So they'll start to show
Banyak
indirectly.
temanku nama
They'll start
Yunis
to
apa
show
lagi ibu,
moderated.
Bu Yunis guru fisika ada,
That,
teman-teman.
particularly at high school,
itu
is most definitely
itu,
high ability
kalau
system.
Pak Yunis yang guru kimia.
Maybe in an undergraduate setting, we might expect
gitu kan,
students to go a bit further.
Yunis cowok, Yunis
To be
cewek.
frank, a student who can represent a circular process of a chemical reaction, a chemical process, that's pretty good. That's high ability. So one way I would argue to push a medium cognitive ability student to a high ability might be to get them to reframe their thinking from chemistry being a linear process to chemistry being a circular process. That would be one way.
Okay.
There was a third question.
Yes. Can I respond to your
Please.
answer? Yes. So for the first answer, it means that we can't collect all the concept map into one, and
Dia
then
cuma sekedar ngambil
we
gelar
can
S3
put
tapi
it
nggak linear dengan kimia.
and then
Kimia
we
kan cuma
can
udah di sini sama
claim
dia.
that as a system thinking. Can we?
Temanku banyak juga
Yeah, I
ngambil di
think so.
Indonesia.
Yeah.
Cerita Pak
If
Rusli
they're
itu
able to,
kayak gitu cerita Pak Rusli. Bu
you're
Eri
looking
yang
for
guru
them
kimia
to,
kayak apa? Emang UNESA ada kimia? Bukan,
you
bukan
may have
kimia.
noticed
Terus
in
yang
those
ini ada
maps,
3 teman kimia
in
ceritain
Sophic,
sama
you can
Pak
do
Rusli.
this. You can
Dia itu
put
ngambilnya
some text
teknologi
over the
pendidikan
arrow.
atau apa kayak gitu kan.
When students draw an arrow between two different components in a concept map, they normally just draw an arrow.
Yes.
They write something as component A, they write something as component B, and they draw an arrow.
Yeah.
In systems thinking, we encourage them to put some text above that arrow to describe that relationship.
Yes.
Because that relationship isn't itself abstract. There's something about that relationship. So being able to describe the purpose and function of that relationship, that interconnection, I think that is one way that you move something from a simple concept back to a system.
Okay, thank you. And for your answer for the third one, so does it mean that every student who can make a circular arrow is considered as a higher thinking system thinking? Because maybe I mean, for example, based on your PowerPoint earlier, there are also like you number the concept is green, yellow, green, and red, like positive, negative, and then neutral. So, for example, if we take that as an example, how will you
yang terbaik itu
classify?
dilihat sama
For
UMK
example,
4,0 semua.
maybe they can give
Suci,
negative
Eka,
impact on
Maya,
the topic.
3 tahun
Maybe
semua
2 or 3
kayak
or
di
more
Citra
than
kan nggak ada
5
saingan dia
or
sendiri
something
terbaik
like
dia.
that. The same.
Putu ada saingannya
Yeah, I do know what you
Citra
mean.
lain kata Putu.
Look, I'm hesitant to saying yes because I know where you're going. I totally agree. Mapping and assessing visualizations is challenging. Students think of the student who is like, oh, I need to write as soon as possible, and they just write. They fill a page. They fill a page with arrows going everywhere and dots going everywhere. And you know the student, right? You know the student, like, they're just putting things on the page because you told them to, and so they don't really know what they're doing. We see these as well. that's why, I mean, there's been books and literature written about this. Some people argue you can't use concept
Tapi
mapping
Bu
for
Fauzana kesayangan
summative
dosen
assessment
killer itu loh.
because it's difficult for
Tris yang
students,
kami
difficult to
dengar.
really get into the
Tapi
minds
suatu hal
of
masuk kan
why
satu
they drew that.
soalnya kesayangannya
We
Bu
would argue
Fauzana
that's
tuh.
why writing text
Aku
above the arrow
aku
helps.
kan kena
But
marah.
I totally agree.
Kalau aku jadi aku takut dengan
One way that we've dealt with it in the past, and Andrew has a good
dia
answer for this,
nyariin
and what Andrew would do
tingginya
is that, again, this is before
udah
Socrates was
kelihatan
out. He was doing everything by hand.
udah kelihatan
The students would make their map, and then it would be like half a page, and then he'd have the second half of the page a text box. So we'd have the students make a map, and then have the students, okay, answer a question based on the map. So the question would be, okay, well, now having made this map, tell me, do you think the Solvay process represents what is sustainable about the Solvay process? How does, so it was a way, and then he would assess summatively the text. They'd have to talk about their map, but, the text became a way of helping them. Other ways of doing it, doing think aloud exercises, think aloud as students are doing the map. Other one to do is, I've seen this done really well, and it was a paper by Mariki's group on this, and Socket lets you do this. Make a map, make a system map that's sort of half complete. So this is a good scaffolding technique. You can make a map for them and leave some gaps. Leave some gaps or leave some arrows. Make a circle that doesn't have any text in it, and then give it to the students and say, you do the rest. You do the rest.
Okay.
And so you fill in the gaps. You make extra connections. And so there's a bit of a scaffold. So that's a way of working with a low to medium student who doesn't know how to make the scaffold. You've given them the scaffold, and now you're looking for the things that they add to that. Socket actually lets you do that. You can actually make one in Socket, save it as a software file, send it to the students, and then they add to it. So we don't have time for that today, but that's a good way that you could make half the map and then have the students add to it. But look, to your main point, concept mapping and therefore systems mapping is difficult summatively. So I would argue it's part of the process. It's a pedagogical tool. It's not the thing you're relying on, it's a thing that you're incorporating into your lesson sequence. It's really great for formative assessment. You challenge the students to make connections that they don't originally see. So that would be a good example of formative assessment. And then you can, as a teacher, start to envisage some of the connections that they're making.
Okay. Okay, thank you so much, Dr. Simos. Yes.
Thank you, Lina.
Thank you very much for the interesting discussion, Dr. Simos and Dr. Lina. As a context, Dr. Simos, in Indonesia is a commonly used concept map as a formative pedagogical tool. So that's why we put a score in every line or a row in Indonesia. So this is the context of the documentations. So maybe the last questions come from Dr. Wata.
Thank you very much, Dr. Ali, for the opportunity. Good morning, Dr. Simus. Thank you very much for a nice presentation. Looking at your presentation, I was wondering, and I'm interested with the system maps that you have already presented, and it has been discussed intensively with Dr. Lina. I was wondering, have you ever done studies where you evaluate the outcomes of the students? I mean, during the classroom, the students discuss to each other, and then of course it will be helped by the teachers. I was wondering what is the outcomes of the learning in terms of the sustainability awareness. Does the sustainability or the green chemistry context just end up in the classroom, or it changes the behavior of the students after they finish the classroom? To put it in the context, Solo, as where the Universitas Plasmar is known as the city where the batik is produced. Batik is like traditional clothes from Indonesia. It used traditional techniques where some industries use the wax to cover the clothes, and then some of the industry use, for example, synthetic dyes which are not treated after they use for the dyeing process. It can be a dilemma for the students, to discuss where the sustainability aspect is, right? It's like society, the environmental, and the economy. And then when we make kind of like a system maps, it can be discussed, it can be marked. But I was wondering if that's enough to change the behavior of the students after they discuss and finish the classroom. There's like a lot of the environmental issues, the society issues that can be discussed actually if we talk about the batik process, especially because I'm teaching the organic chemistry, and then one of the topic is the electrophilic substitution reaction, where you could like make dyes from, for example, petroleum derived dyes like azo dyes. So we try to find the alternative synthetic route to find like the better reaction where it has lower impact to the environment, or even we isolate the natural dyes from nature. I would like to know your perspective on that issues. Thank you very much.
Thank you so much for that was I'd really love to know more about that. I've just put my email in the chat, and you're more than welcome to email me. Well, by the way, anyone is more than welcome to email me afterwards and keep in contact with me. Yeah, I think to your question about do we have evidence that students are changing their behaviours, I think it's too early to tell. I think the fact that they're talking about, wow, the sustainability is actually something that we need to talk about when it comes to chemistry. I guess that in itself is a change in behaviour. But if they're changing their everyday experiences, are they more conscious? Are they making different consumer choices? I guess to your example, are they making different consumer choices because of that? I think the evidence is not super strong yet, but it's very early days. I was fortunate enough to, one example I can give you is I gave a talk 2 years ago, the previous World Chemistry Congress when it was in The Hague, and the co-presenter at the same symposium was someone from South Africa, and she was talking about the use of soaps and surfactants and the impact that it was having on the local water supplies for shanty towns. And she was saying that students who were doing these maps and doing these activities in the classroom, these were undergraduate students, they were telling the teacher, they were telling Lynn that they were going home and telling their parents, saying, hey, this is bad. This is how, these are the things that are having an impact on the local water supply that are getting into our local streams, and they were pushing their parents, pushing their families to change the type of detergents and soaps that they were using. So I get it's how far much of a follow-up do you want to do? How far do you go in modelling and mapping changes of behaviour? It's a very good psychosocial question. There are some psychometric measures of change of behaviour, but we have not looked at that. I won't pretend that we've looked at that in detail. It's certainly something to think about when we do follow-up. We're currently doing follow-up with teachers who were in that 2020 workshop, and we're writing that up at the moment with Madeline. Interested to see if they feel as well that behaviours have changed. But it's a really good question. I'd love to give you a better answer than that, but I think it's certainly something that will happen. We just need evidence of it.
Okay, thank you very much for the questions and the answer, Dr. Seamus. And one additional question, maybe, Dr. Seamus, from Professor Anthony in the chat box. Dr. Anthony asked that, based on your experience, what are the main difficulties of students in using system thinking in chemistry? And then what is your suggestion related to the learning strategies to enhance their system thinking skills?
I think most definitely for me, this is a personal view. I think that one of the main difficulties that students have is the same view that teachers have, is making social scientific connections to the chemistry. You know, you can imagine you're in a classroom, you tell the students, right, you know, come up with 5 environmental factors, come up with 5 social factors, you know, that are related to this chemical equation. And they just stare at you blankly. And, you know, so I think, and teachers do the same. So what do we do when we run professional education workshops with teachers? What do? We tell them to get out their phones, to get out their devices, do some digging around, do some learning. So there's a bit of research involved. So I would definitely say that's an early initial barrier for the students, that the answer's not in the textbook, that, you know, they do need to go look at some other material, they need to get online, they need to do some research. So I'm not part of those studies, but I've seen studies in the past that have shown that students do struggle sometimes to do independent research. In Victoria and Australia right now, we're moving towards a pedagogical learning model. It's called Learning Model 2.0, where all teachers are being professionally trained on it right now. And one of the aspects of that is that we don't do independent student research straight away. We take a guided approach. So the teachers have to do some of that initial research with the students. So that's one way that you could support the students early to do some of that research of context that is not in the textbook. But where are you going to go find out about ethical factors? Where are you going to go find out about, you know, the circular aspect of some of these chemical equations? You have to go do some research. So teachers have a role and responsibility to guide some of that initial research. A quick AI Rotu. One thing that we found, I do it myself, is AI and ChatGPT can be a nifty, I won't say fantastic, but a nifty, an excellent way of getting some surface level understanding of some of those social, economic, environmental factors that don't immediately become apparent to the student. Because of course the teachers know them, so why would the student? So teachers getting on to AI, asking it, okay, I've got this chemical equation, this is the product, give me 3 economic, give me 3 ethical factors. The answer that ChatGPT, the answer that AI gives is going to be very, very surface level. It's going to be very, very basic, you know, dot points. But that's enough for a student to start with. That's enough for a student to think about, right, now I know what I need to go look for. I'm going to go look for that. And they're going to go look for more authentic sources. So it comes with its own challenges. You know, what if ChatGPT gives them a ridiculous answer, a bogus answer, and, you know, leads them down the wrong rabbit hole? But, you know, I think for the most part, ChatGPT is going to give them an answer comparable to Wikipedia. So it's a place to start. They could use that as a way of getting some service level, basic connections that aren't the answer's not in the textbook. The answer's not. They don't know what to search for on Google. So they could use AI to get some initial factors, and then they explore those in more detail.
Okay, thank you very much for the answer, Professor Anthony. Is that enough?
Yeah, okay.
Okay.
We can chat about this more soon, Anthony. But absolutely, I do appreciate the nature of the question, and supporting students at that initial stage is certainly an important factor.
Okay, thank you very much, Dr. Seamus and Professor Anthony. So we come from the end of the sessions because don't ruin your day today because you have a flight after this session,
really
right?
But thank you so much. Yeah.
Okay, and as a committee, as a committee, we would like to thank you very much for your contribution in this CEC 2025. And maybe we can meet in person in the next editions, right? Okay, thank you very much, Dr. Seamus, and for all of the participants, give applause for Dr. Seamus. Okay,
Thank you, everyone,
thank you,
and
thank you.
have a fantastic 2 days. All right, bye for now.
All right, thank you so much, Dr. Dani, for your valuable insights and a fantastic opening sessions. And for all participants, we have 5 minutes breaks before the session 2. Don't forget to fill the attendance list that already sent in chat box. And if you want to make cup of tea or want to go to the restroom, please do so.
Nabung dari Shopee affiliate itu Bu Retna, komisinya baru 300. Nanti kalau ada berapa juta itu baru mau belikan HP. Udah kangen laku paling sehari komisi 300.000 gitu, gak seberapa receh. Belum jutaan kayak si Pella belum. Iya, kalau gaji 7.500 dia udah tinggi. Aku pikir nanti kalau udah jutaan lah baru buat beli HP. Dicek hari ini, oh masih 300.000 komisinya. Iya, itu padahal videonya udah banyak banget, tapi yang laku ya 100 rupiah, 200, mau receh-receh lah, 500. Pokoknya di kamar Mbak Nana itu ada apa aku pinjemin. Dia rajin beli kosmetik apa aku pinjam untuk apa Maybelline lah apa untuk buat konten bener. Terus ini ada koper, aku pinjam koper, ada makanan, ada yang hijau-hijau tuh. Serbu apa aku buat konten semua. Nggak tahu kapan lakunya, mana rezekinya, kok rezeki dapat.